Hello, fellow pedestrians. In this last stretch of the differential equations, we're going to apply all the theory that we've learned about to some concrete examples and see how these ideas will manifest in practice. So let's go ahead and start with a very infamous example. So let's say we have the differential equation y prime prime plus y prime plus x squared y is equal to 0. Now, let's check for singularities first. So xpx, when x goes to 0, assuming that we are expanding around 0, but this is not the case, it's just that 0 is the only possible singularity here. Now, this is just 1, because p is 1 over x, so times x, this is 1. So it's finite, and likewise x squared p of x is going to be 0 for x going to 0. Hence, x naught at 0 is a regular singularity. Right? Now, let's go ahead and plug the Frobenius in this differential equation. What we have is the sum starting at 0 to infinity of AL k plus L k plus L minus 1 x to the k plus L. This was this term, so plus this term AL, of course, from 0 to infinity of x to k plus L again, and the last term AL x to the k plus L plus 2, and this is 0. Now, the lowest term, which is x to the k, is realizable for L is equal to 0, like usually. So what happens is that you will get a naught of k times k minus 1 plus k is equal to 0. And again, this cannot be 0, as one of the first assumptions in the Frobenius method, meaning that k squared is 0. And this is a double root, right? So we are only expecting one solution only is given from Frobenius. One linearly dependent solution, that is. This happens every time when we have a double root as a solution to the indicial equation. As we've said, this is called the indicial equation, and its roots say a lot about the behavior of the series, as we've said in the previous lecture. So, having a double root, meaning that also what this translates to is that y1, the solution that given from Frobenius, is going to be constant. Around 0, while y2 is going to diverge. Now, we see there is a gap of 2, so let's check what happens at the next lowest term, which is k plus 1, which will manifest for close to 1, and this again, this and these terms, this starts at x of k plus 2. So a1 k plus 1 times k plus k plus 1 is 0, meaning that a1 k plus 1 squared is 0. So for k is 0 that we found, this cannot be 0. What that means is a1 is 0. Right? It cannot be arbitrary, it can only be 0 in this case. And finally, let's go ahead and do some shifting in our differential equation. We go ahead and shift this to j, likewise, and shift this to j minus 2. And now we are able to find, dropping the sums and having the net coefficients will lead to the recursion relation that is given by a j of, let's go ahead and plug k equals 0. This is the only solution, so j times j minus 1 plus j plus a of j minus 2, this term. And this is 0. And this can be rewritten as a j is equal to minus a of j minus 2 over j squared. And this here is our recurrence relation. So let's go ahead and plug some values in here and see what that leads us. So for j is equal to 2, we have a of 2 is minus a of naught over 4. For j is equal to 4, a of 4 is going to be minus a 2 over 16, which can be rewritten as a naught over 64. And lastly, let's do one more. A 6 is just minus a 4 over 36, which is equal to a naught over, this can be written as 2 squared, 4 squared, and 6 squared. Likewise, this is nothing more than this is 4 squared, right? And also 2 squared. And this is of course 2 squared again. So it's very easy to find a pattern here and check that a general solution, a general way of writing the coefficients, which we can see that we only have even coefficients. Why? Because a1 is 0, and the recurrence relation says that there is a gap of 2, there is a step of 2 here, so y3 is going to depend on y1. A1, sorry, A3 is going to depend on A1, but A1 is 0, so A3 is 0. Likewise, A5 is 0, so every odd term is going to drop out, it's going to vanish. So we only have even terms that are going to be written as, oops, there's a minus here. They're going to be written as we have a naught on the denominator, and also have a flipping sign, and the denominator is just the multiplication of its next power. So you can see that this is 2 squared, this is 2 times 4 squared, this is 2 times 4 times 6 squared, so this is going to be 2 times 4 times 2n minus 2 times 2n, and all of this is squared, right? So this is written again. If we take out of the parentheses, it's 2, so we have 2, but there are 2n of these terms, so 2 to the 2n, and inside we're going to have 1 times 2 times 3 times all the way up to the n, and this is just n factorial squared, right? And this is the general way to write down the coefficients. So finally, first solution that is given by Frobenius is going to be y of 1 of x is equal to the sum of al x to the l plus k and k0, meaning that this is just a naught 1 minus x squared over 4 plus x fourth to the over 64, etc. And this again the sum of minus 1 to the n of x over 2 to the 2n over n factorial squared. So these two, this parenthesis came from here, right? And this is our solution to this differential equation. Now, this solution is widely known as zeroth first kind Bessel function, and is widely denoted as j of 0, right? And has many applications in physics also. Now, let's see what happens when we try to check the convergence of the series, because, like we said, we expect the interval of convergence to be all of R. Why? Because there is only one regular singular solution, and this should be a radius of convergence. So let's move on to our Python file and check what happens there. Now, for starters, let's import from mpmath, import mp. This is a Python library for arbitrary precision arithmetic. So what it does best is, assume that you have a series you want to be summed upon. You're going to be able to set a very high precision, or else you're going to get results that are not realistic at all. What I mean by that, imagine that I'm going to set TPS to 50. What that does, it sets precision level to 50 decimal places, right? So it really controls the number of decimal places used in computations. And setting this to a number changes the precision of floating points in calculation. Now, let's go ahead and define our main function, which is going to call some series. Going to get a function as a variable, and also some points, the x point, the x naught point, and some terms that we are going to sum. So the total is going to be just 0, and x naught going to be redefined as mpf of x and mpf of x naught. Again, what that does is that mpf represents a floating point number with arbitrary precision. It's very similar to Python's float, but with more precision. And it also respects the precision that is set here. So why this is really important? Because when you are calculating and summing series, rounding and rounding that is going to happen at very large floating points is going to be respected here. But if you do not do that, then you're going to probably get something that will diverge, that will falsely diverge. But in reality, it should be converging. So we're going to see an example of how that works. And okay, now let's go and make a for loop for n in range of the terms. So starting and summing, we're going to have a term. Let's call it term is going to be, this is a series function that we're going to, it will change for every time. So x will have these variables. And lastly, I'm just going to add to the total the term we just found and return our total. Now let's also just set this to MPF 0 for consistency, because it will just would only use it as an integer. It could work, I don't know, but let's just be sure. Now we saw the Bessel function. Let's define that, and x naught. We saw that the Bessel function can be written as -1. So let's just return -1 to the n times x over 2 to the 2n over factorial of n squared. And that's it. Now let's go ahead and set some values. So this is going to be the x value, going to be the x naught value, and the terms to sum. And let's just start from, let's say, 1. We expand around 0, and what happens for 1000 terms, precision. And set the result as the sum series of Bessel for x value, x naught value, and terms to sum. And finally, let's print that. So the sum of the series for x equals to x value going to be is the result. And let's see what that gives us. It's a perfectly normal number. There is no divergence whatsoever. Let's just fix let's just modify this so it will only print out, let's say, 10 decimal points. Yeah, and voila. Now let's go ahead and find what happens at x equals 10. Perfectly convergent at the 100, the 1000. So what happens here is there is divergence. Why is that? We were promised that this series is totally convergent. It is well defined in all of R, from -infinity to +infinity. So why does this happen? This is due to probably having a small number of terms that we are summing. So if we trickle this a little bit, so what you can do is growing the number of terms to sum, or also growing the precision. So let's try that first. Doesn't work. Let's go ahead and also amplify this. Now it will take some extra time depending on your machine, but I hope it will eventually run. And there you have it. So the rounding gaps that are happening inside the sum are not properly managed when you have a small number of decimal places regarded. But when you go ahead and amplify this number, or taking more terms into consideration, then you will indeed take the correct number. And a way to check if this is really the correct number, is go ahead and check Wolfram. It was 0.024, and if you compute that, it is indeed this number. So for 100, if we compute this, this is 0.1998. So 100 will give us, 100 0.1998, exactly the same number. So the series is totally divergent as promised. Now let's head back to our blackboard and continue with our analysis. So what we had here, we found the first solution and we convinced ourselves it is indeed convergent everywhere as promised. Now you can also see that if you take the ratio as known going to infinity of un plus 1 over un, now that you have the solution, and if you do the calculation, you will see that this will go to 0, meaning that the radius of convergence is infinity, which is also means that it converges around 0 everywhere, as expected. Now, let's go ahead and find ourselves a second solution, which we know that cannot be found using Frobenius. So for a second solution, we show that it can be given by this formula, this y1 integral of e to the minus p dx over y1 squared dx, right? And what is p? Is just 1 over x, right? Meaning that this can be written as y1 integral of 1 over x, because this is 1 over x is going to be ln. If I do it analytically, you'll see that this is e to the minus dx over x, which is written as e to the minus ln of x, and this goes here, leaving you with 1 over x, right? So 1 over x and y1 to the minus 2 dx. Now, what we have here is a series, and the way to use the series in an integral, and this is very educational for general purposes, is by using something called the binomial expansion, which is given by, let's say, 1 plus u to the r is a sum from n 0 to infinity of Rn, this is called the binomial coefficient, x to the n. And the binomial coefficient is given by r times r minus 1, dot all the way r minus n plus 1 over n factorial. So, since we know what y1 looks, which is, if we expand this is nothing more than this guy here that we wrote. So this, using the binomial expansion, will be written as, so y1 to the minus 2 is 1 minus x squared over 4 plus the fourth 64 minus 2, and using the binomial expansion, we'll get 1 plus minus x squared over 2 plus x fourth over 64 times minus 2 plus minus 2 times minus 3 over 2 factorial. This will cancel out, and minus x squared over 4 plus x to the fourth squared, and let's keep up to the fourth order, and this will give us eventually, if you do the calculation, 1 plus x squared over 2 plus 5x to the fourth over 64 plus higher order terms, 6th, 8th, and etc. Now, we must check every time for singularities or divergences after integrating. Since the binomial expansion is only defined absolute x being less than 1. Okay, that does not really concern us in our case, but we do really have to check every time. So if this is 1 and plug this in 1, we'll finally get that y2 of x is just y1, and the y1 we denote it as the Bessel function of 0, so let's just write it this way. And integral of 1 over x, this is the 1 over x, and this was given by our binomial expansion, so 1 plus x squared over 2 plus 5 over 64, etc. And finally, if you do the calculation, you'll find that this is j1, this is ln of x, second term is x over 2, which is just x squared over 4, plus 5x to the fourth over 128, plus higher order terms. And that's it. And of course, this is a totally linearly independent solution that diverges at the origin as expected, since the root of the initial equation is 0, right? Now, Bessel functions are in general of great importance in physics, so they arise in many concepts like quantum mechanics when solving Schrödinger's equation in cylindrical or spherical coordinates, or also in hydrogen-like atoms and many other cases as well. So now we are done with it. Let's go ahead and check another example. So let's say we have squared minus 9x to the fourth y prime prime plus minus 6x y prime plus 10y is equal to 0. Now the x is going to be written as minus 6x over x squared 1 minus 3x squared. So this cancels out, so minus 6, and let's divide with 9. Going to get this was going to be 1 over 3 minus x times 1 over 3 plus x, right? And what happens if we try to expand around to 0? So the possible candidates to be singularities are 0, 1/3, and minus 1/3, right? Now, let's check what happens at 0. This entity, when x going to 0, is just going to be minus x over 9 over 1/3 squared, and this is just a finite number. We don't really even need to calculate this, so this is finite. And x squared to x, which is going to be written in the same way the analysis, is also going to be a totally fine number. We're not going to do all the calculations, not really needed. So if you do exactly the same for, let's say, this is for x naught is 0, you do exactly the same for x naught is 1/3 and for x naught is minus 1/3. You will find for each case, so here what you're going to do is x minus 1/3 over px and x minus 1/3 squared over qx, etc. So if you do all this, what you'll find is that all of these points are indeed regular singular points. So we can say that x naught 0, minus 1/3, and 1/3 are all regular singular points, right? And what we've said, when we are expanding around a singular point, then we know that, let's say we expand around x naught is equal to 0, which is usually the case in Frobenius. Of course, you could be asked differently, or you could experiment and go ahead and expand around 1/3. So we would have something like this, right, as a solution, plus k. But we just usually expand around 0. So expanding around 0 for this particular case means that a radius of convergence is going to be x naught minus r naught and x naught plus r, where r is the distance to the closest singular points, right, which is 1/3. So this translates to, this is 0, 1/3 until 0, and 0 until 1/3. So what happens at 0 is going to be defined by the positiveness of the initial equation. So let's go ahead and try and solve this equation. So we have the sum of AL k plus L times k plus L minus 1 next to the k plus L minus 9 AL k plus L k plus L minus 1 next to the k plus L plus 2 minus 6 AL k plus L next to the k plus L, and finally plus 10 AL next to the k plus L. It's 0. Now, let's go ahead and see what happens at the lowest term, which is next to the k, and is realizable for x equals to 0. So this translates to a naught. So we have this and this and these terms that play a part here. So what we have is k times k minus 1 from here, minus 6 times k, and plus 10. It's going to be 0. And this leads us to a quadratic equation, minus 7k plus 10 is equal to 0, which has roots 5 and 2, and they're both positive. What that translates to is that if we take this into account and we link to this, then this translates to minus, meaning that it would totally converge at 0. It will just give us a constant, right? Now, let's see what happens at the next lowest term, which is x to the k plus 1. Again, this is realizable for L is equal to 1, meaning that we're going to get, again, these three terms. This is out of the question. This starts at k plus 2. So we have a 1 times k plus 1 k minus 6 times k plus 1 plus 10. This is 0. Now, you go ahead and plug this 5 or 2 in this equation, both will get you that this is non-zero. So this is different than 0 either for 5 or for 2. What that means is that A1 is 0. There's no other way around it. Because, again, the solutions of the initial equation, which are 5 and 2, if we plug them in here, this will be a non-zero entity, non-zero term, meaning that this is 0. Right? And let's go ahead and plug some values. Let's start with the bigger one. So for k is equal to 5, go to our differential equation, and as we know, we shift L to J, L to J minus 2, L to J, and L to J. This is L to J. Right? And what you will get is a J times 5 plus J times 4 plus J minus 9J minus 2 of 3 plus J times 2 plus J minus 6AJ of 5 plus J, and plus 10 times AJ is going to be 0. And if you do all the calculation, you will end up with a recurrence relation of this form. AJ is going to be 9, 2 plus J over J, AJ minus 2, right? And again, we see that there's a step of 2 here, meaning that all of the odd terms are going to be 0. So A3 is going to depend on A1 by this recurrence relation, so all of the odd terms are 0, right? So let's go ahead and try ourselves finding pattern. So for J is equal to 2, we get that A2 is 9 times 4 over 2 is 0, so just 18. So if we rewrite it, can be written as 8 to the 1 times 2 A0. Now for J is equal to 4, A4 is just going to be 9 times 6 times over 4 times 18 A0. So this is going to be a squared, and 2 times this is 3, so just a 9 squared times 3 A0. And I hope you see a pattern. So for J is equal to 6, we get A6 going to be again A to the third times 4 times A0. And there is a pattern here. For all the even terms, we have 9 to half, so this is squared, which is half of this. This is 1, which is half of this. This is 3, which is half of this. So we have 9 to the half of this, so n. And what that number is, we have 2, 3, and 4. So this is just half of this plus 1. This is just half of this, which is 3 plus 1. So half of this plus 1. And there you have it. And the solution, pretty easy to find, it's just AL x to the k, x to the L plus 5, which is the k. So finally, just a 0 sum from n to 0 to infinity of 9 to the n times n plus 1 times x to the 2n plus 5. And this is our solution, given by Frobenius. Now, we can also use Python to see what happens for this solution. If the interval of convergence that we say that is the interval of convergence is really true for what we said. So here we are in our code editor where we left off, and let's check what happens for our newly designed function. So let's call it just example 1, set our variables, and return. The function was 9 to the n, uh, times n plus 1 times x to the 2n plus 5, right? And we were promised that this would totally converge for values of x between minus 1 over 3 and until 1 over 3. So let's go ahead and check. So let's do this for our example. Go ahead and check what happens at 0. At 0, this is 0, which is totally fine and totally expected, right? So what happens at 0.2? This should also converge, and it totally does. What happens at 0.3? This should also converge. Totally does. What happens at 0.4, which is outside of the radius, because the radius is 1/3, which is 0.33333. So what happens little outside of the radius? Now you can see that such a small change, going from 0.3 to 0.4, the first one would give something very close to 0, and the second would give you something very close to infinity. I mean, this is a number with 1500 zeros after it. So very huge number. It greatly diverges. There is a great divergent catastrophe here. So it indeed works, and it works like a charm. It works greatly. Now let's head back and check what happens for the second root of the initial equation, right? Because we did use that, but what happens here? Can Frobenius actually provide with a second solution? When we have a difference, when the difference of the roots of the initial equation is non-zero, we are promised at least one solution, but can we get a second solution that is linearly independent to the first one? So let's go ahead and plug 2 like before. So what we get is plus j, 1 plus j, minus 9 times aj minus 2, j minus 1, minus 6, aj, 2 plus j plus 10 times aj, and this is 0. And again, I'm going to end up with a recurrence relation after do the calculation that is aj is 9 times j minus 1 over j minus 3 times aj minus 2, right? And if you do all the same reasoning and go ahead and plug A2, A4, and A6, where we'll end up with this kind of relation. So minus 9 to the n, 2n minus 1, A0. It's very similar to the one we found here, which was, where is it? Here. This was our solution for the terms, whereas for k is equal to 2, this is the solution of the terms. So in exactly the same fashion, y2 of x is going to be sum of al x to the l plus 2 here, because k is 2, and this translates to minus a0, so we don't really care, this is just a constant. sum of a to the n, 2n minus 1, x to the 2n plus 2, which is linearly dependent to y1, since the lowest terms of x differs. So the lowest term here is x to the 5th, while this is x squared. And there again, so a second solution, a second linearly dependent solution, is provided from Frobenius, where we have two integer solutions which are different to each other, right? And again, if you go ahead and try this in Python, you will get the same results, meaning that it will diverge for the same promised interval. So outside of 1/3 and lower than -1/3, it will totally diverge. It's exactly the same thing. So let's go ahead and check another example. Now, let us move on to another example, which is very interesting to see. Let's say we have x squared y prime prime plus x minus x to the 4th y prime plus 3x cubed y is equal to 0. Now, again is 1 over x minus x squared, while q 3x, right? So what happens at x and what happens at 1, because no, basically we only have 0 as a potential singular point. So at 0, this is just 1 minus x cubed, and when this goes to 0, this is just 1, which is finite. And again, x squared q, when x goes to 0, is 3 times x cubed, right? So again, finite, meaning that at the point 0, this is an irregular singularity. And if we decide to expand our series around this point, then by theory we know that we'll have these intervals as our intervals of convergence for the series, right? And we'll examine later what will happen at this point of 0. Now, let's go ahead and apply Frobenius. So we have sum of L k plus L, k plus L minus 1, x to the k plus L, plus AL k plus L, x to the k plus L, this term, so minus AL k plus L, x to the k plus L plus 3, plus final term AL x to the k plus L plus 3 again, and this is 0. Now, the lowest terms that arise from these two, which are these are the lowest terms, and are realized by L is equal to 0. So what we're going to have is a naught of k times k minus 1 plus k is equal to 0, or that just k squared 0. So this is a double root, meaning that we can only get one linear independent solution using Frobenius. What it also means is that this is going to be written, because it's non-negative, as all of R. Why? Because at the point 0, since this is 0, and for 0 and negative, the series does not diverge, meaning that the series will converge everywhere for every single x. Now, you can see that there is a huge gap between the first and the second possible powers of x. So we can also check xk plus 1 and also xk plus 2. This is a first. So for L equals to 1, what we will get at the end is that a1 of 1 plus k squared is 0. So for k0, this is not 0. That means that a1 is 0. So this is the root. This is information about the first non-zero, which is 0 term. And for L is equal to 2, again, a2k plus 2 squared is 0. So again, this is not 0, meaning that a2 is also 0. And this will prove to be very useful information. You will see immediately why. So we're going to our differential. We go ahead and send this to j, send this to j, send L to j minus 3, and again L to j minus 3. And if we plug all this, what we will get for a recurrence relation, so we get j times j minus 1 plus j plus a of j minus 3 of 3 minus j minus 3, which is equal to 0. And finally, we'll end up with a recurrence relation of j minus 6 over j squared times a j minus 3. And this is the recurrence relation. Now, this is a very interesting example. Why? Because let's go ahead and set j is equal to 3. What we're going to get is a3 is minus 3 over 9, so minus a0 over 3. And we are done. Why? Because a4 is going to depend on a1, sorry. But a1 is 0 on a1, so a4 is 0. Also, a5 is going to depend on a2, which we also found that is 0. And a6 is going to depend on a3, which is not 0, but a6, if you plug 6 here, is actually 0 by itself. What that means is that every other term that comes after a6 is also going to be 0. Why? Because 3 continuous terms are 0, and there is a step of 3 in the recurrence relation. So a7, which depends on a4, is 0, a8 that depends on a5 is 0, and so on and so forth. Hence, the only terms that survive are just a0 and a3. What that means is that our solution is just going to be the sum al x to the k plus l. K is 0, so a to the l is going to just be a0 plus a3 x to the third, right? Which can be finally written as 1 minus x cubed over 3 from here. And this is the only solution that Frobenius will be able to derive, right? And you can see that this is a polynomial, of course. What that means is it is, of course, described over all real numbers. But this is just a coincidence, because we'll see a next example And it is a coincidence because we found that the interval of convergence is all of R, and since we have a series that is truncated to a polynomial, of course it's going to coincide. So we can check another example where this will not be the case. So x squared y prime prime minus xy prime plus 1 over 1 minus xy equal to 0. Again, we can easily check that x naught 0 is a regular singular point. Let's not do this again and again. And x naught at 1 is also a regular singular point coming from here. So if we expand around x around 0, what we are going to get, that is given from theory, is that we have 0 minus r, and r is the distance. So let me write this down. Let's write this as x1. So if we expand around x naught, that makes the interval of convergence to be x naught minus r naught, and also x naught plus r, where r is the distance to the nearest singular point, which is 1. So this is written as minus 1, 0, and 0, 1. So, and if we find the root of the initial equation to be 0 or positive, then the interval of convergence is going to be minus 1, 1, which will be the case. So stay with me for a moment. Let's go and apply Frobenius to this differential. We're going to have L times K plus L times K plus L minus 1 x to the K plus L minus AL K plus L K plus L minus 1 x to the K plus L plus 1 minus AL K plus L x to the K plus L plus a lot of terms, AL K plus L x to the K plus L plus 1, and the final one, AL x to the K plus L. And this is equal to 0. So for the lowest term, which is x of k, like we know, we're going to have that a naught of k times k minus 1 minus k plus 1 is 0. And this is just written as k minus 1 squared is 0, since again this is not 0. What that means is we have a double root that is 1, and since this is positive, then this is, sorry, meaning that this is our interval of convergence. Now, let's go ahead and find what happens. So, this goes to j, this goes to j minus 1, this goes to j, this goes to j minus 1, and this goes to j. And we have a j times j plus 1 j minus j plus 1 plus 1 minus a of j minus 1 times j minus 1 j minus j, and this is equal to 0. And finally, we will end up with this recursive relation, a of j minus 1. This is a relation. Now, let's go ahead and find some numbers here. So, if we plug 1, a of 1 is going to be, this is minus 1, so minus a of 0. A of 2 is going to be 0 if you plug 2 here. But since all other terms, because there is only step 1 here, so A3 is going to depend on A2 and all the way up to the last term. Of course, there is no last term. So what we have, our solution, is just AL x to the k plus L, and k is 1, so L plus 1, meaning that we have only the first two, so A0 x plus A1 x squared. This can be written as A0 of x1 minus, and this is our final solution. If you plug this, this is a solution to our differential equation. Now, this is a polynomial, so we had again a series that is truncated to a polynomial. The big difference is that this works everywhere and not just here. So, like we said in when we were showing all our theory, is that when a series is truncated to a polynomial, then the interval of convergence that is supposed to be the real interval is not really applicable. As we can see here, this works everywhere and not just here, right? Now, let's just for fun try and find the second solution. This is just y1 to the minus p dx over y1 squared dx, and this is y1. Now p is just 1 minus 1 over x, so we'll end up with 1 over x finally, and this is our final solution. Now, like we know, let's just stop here and try to write this as a binomial expression. So we know that 1 plus u to the n is just the sum of Rn from n goes from 0 to infinity of this is R of and x of n. So this is just x minus x squared. Wait, actually, no, this is not true, because this is minus of minus 1 over x. So imagine this is x to the minus, so dx over x, meaning that it's just e2 ln x, which is just x, meaning that we have x to the minus 2 times 1 minus x to the minus 2, right? Dx. So finally, we have y1 integral of 1 over x, 1 minus x to the minus 2. So, according to this can be written as 1 minus x to the minus 2 is the sum of minus 2 and xn. And these coefficients can be written as minus 2 times, and this is also, have a minus again. So let me correct this. So minus n x to the n, since there is a minus here. So this is minus 2 times minus 3 times all the way up to minus 1 minus n over n squared, right? Which is minus 1 to the n, taking all the minus 1 terms, and what is remaining is just the factorial of n plus 1 over n factorial, which is nothing more than minus 1 to the n of n plus 1. So this can be rewritten as n we have minus 1 to the 2n, which is always plus. So what that leaves us is n plus 1 of x to the n, from 0 to infinity. So what this really is 1 plus 2x plus 3x squared, etc. So our final solution is finally going to be written as this is just x times x minus 1, like we found, and this is written as this guy. So 1 over x times 1 plus 2x plus 3x squared plus higher order terms to the fourth, etc. dx, and finally times ln x plus 2x plus 3x squared over 2, etc., which diverges at the origin as expected, right? Now, let's move on to the most complicated example we're going to try to tackle and find solutions, which is called the Legendre differential equation, which is written as 1 minus x squared y prime prime minus 2xy prime plus lambda y 0. Now, the x is going to be minus 2x over 1 minus x squared. So plus and minus 1 are the poles, and also u of x is lambda 1 minus x squared. So again, for, let's say, at 1 of px, when x goes to 1, this is just 2x over 1 plus x, which goes to 1. Likewise, squared of qx, just written as minus lambda of x minus 1 over 1 plus x, and goes to 0, and they're both finite. So x at 1 is a regular singular point. Likewise, we will find that also minus 1 is a regular singular point. So they're both regular singular points. Now, hence, the interval of convergence when expanding around x0 is again minus r. Now you can see that we do not exclude x0 because x0 is an ordinary point. It's not a singularity at all. Meaning, we just have this as our interval of convergence. Every value outside of this interval is going to get our series to blow up, right? So of course, as we already seen, functions that have a constant, like this one that has lambda, are more susceptible to further investigation, right? So let's go ahead and apply Frobenius and see what happens. So a of L, k plus L, k plus L minus 1, x to the k plus L minus 2, minus AL k plus L, k plus L minus 1, x to the k plus L, minus 2 times this term, AL k plus L, x to the k plus L, and finally of lambda AL x to the k plus L. This is 0. Now, for L equal to 0, for the lowest term, we get that a naught of k times k minus 1 is going to be 0. Hence, we got two roots, which are 0 and 1. Now, if we check the next term, which is x at k minus 1, we'll find that a1 times k plus 1 is 0, which means that a1 is 0 when k is 1, because k is 1 keeps this different than 0, while a1 is arbitrary for k is equal to 0. Now, we're going to check the case k is equal to 0. So we can take all the possible terms and not use the second root of the initial equation. So what we have, now let's go ahead and do what we always do. Take this and send this to j plus 2, this to j, L to j, and L to j again. So for k is equal to 0, we have a of j plus 2 times j plus 2, j plus 1, minus aj, j times j minus 1, minus 2 times aj, j, plus lambda aj, and this is 0. And if you rewrite this, you will get the recursion relation that is a of j plus 2 is equal to aj times j plus 1 minus lambda over j plus 1 times j plus 2. So this is the recursion relation, and let's go and find out what the values does this take. So for j is equal to 0, a2 is going to be a0 minus lambda over 2. For j is equal to 1, now the odd values do survive because a1 is arbitrary, so a3 is going to be minus a1 lambda minus 2 over 6. For j is equal to 2, a4 is a2 times 6 minus lambda over 12, which is written as a0 lambda times lambda minus 6 over 24. For j is equal to 3, a5 is a3 12 minus lambda over 20, which is lambda minus 2 times lambda minus 12 over 120 a0. And let's do a couple more. For j is equal to 4, a6 is a4 20 minus lambda over 30, which is minus a0 lambda times lambda minus 6 times lambda minus 20 over 720. And a last one, for j is equal to 5, a7 going to be a5 30 minus lambda over 42, or minus a0 lambda minus 2 lambda minus 12 times lambda minus 30 over 5040. Now, we have both odd and even terms. So let's go ahead and mark the even terms with red. So a2 is this, a4 is this, and a6 is this. And with green for the odd terms. So a3, a5, and a7. And let's see if we are able to recognize a pattern here. So for the odd terms, so 2n, we have again a flipping sign, so we're pretty used to it. And in the numerator, we have some particular products that will go like this. It's going to be lambda times lambda minus 6 times lambda minus 20 times all the way up to lambda minus 2 times n by 1 and 2n minus 1. Of course, this is not this cannot be immediately seen, but if you go ahead and investigate it a little further, you'll see that indeed it works for its n. Now, in the denominator, it's very easier to see that you just have the factorial of the order. So this is factorial of 5, and this is the same deal with the odd numbers. So also this is the factorial. This is the factorial of 4, right? So we have is the factorial of this, which is 2. What am I doing? It's just 2n factorial. So likewise, for the even terms, for the odd terms, sorry, we have minus 1 to the n, and we have a nominator that looks like this: lambda minus 2 times lambda minus 12 all the way to lambda minus 2n times 2n minus 1. So the only difference is that here we have n minus 1 and n. This will greatly helps us when we're going to apply this in Python. So, and the denominator is of the same logic. So we have just the factorial of the order. That's it, right? Now, let's see how the solutions are going to be written now. So y of x is, let's take the even terms that depend on 0. So the sum from 0 to infinity, and we have minus 1 to the n, a multiplicative product going from 1 to n of lambda minus 2 times k minus 1 times 2k minus 1 over 2n. Sorry. Over 2n factorial and x to the 2n. Right? But we've used that k0, so this remains as x to the 2n. Likewise, we're going to have a sum from 0 to infinity of minus 1 to the n, and again a multiplicative product going from 1 to n of lambda minus 2k times 2k minus 1. And again, the denominator is 2n plus 1 factorial and x to the 2n plus 1. Now, we call this the even part, and we're going to call this the odd part. So you can easily see that if you're going to rewrite them, the even part is just 1 minus lambda x squared over 2 plus lambda times lambda minus 6 over 24 x to the 4th minus lambda times lambda minus 6 times lambda minus 20 over 720 to the 6th, and so on, while the odd part is just x minus lambda minus 2 over 6 x cubed plus lambda minus 2 times lambda minus 12 over 120 times x to the 5th, and more terms that I'm not going to write, right? So we see that we do have a set of solutions that are linearly independent. And how do we know this? Because the lowest term of these two solutions are different. This starts at 0, while this starts at x. So they are indeed linearly independent solutions. Now, what is of great, very interesting to see, what happens. Let's do some investigation here. What happens if we require that a of j plus 2 is 0? What that means is, if you check our recursion relation, so meaning if this is 0, so the next term is going to be 0, meaning that lambda can be, would only take specific values. So we know that j are just integers. So what that means is that we can set, let's say this is m, to use a different notation. So the lambda of m is going to take these values. So the multiplication product of two continuous integers. And if you check this, so for m is equal to 0, this is 0. For 1, this is 2. For 3, this is 6. For 4, this is 12. And so on and so forth, right? For 1, this is 2. For this is, yeah, whatever. I don't know what am I doing. I just jumped, leaped over an integer. For 2, this is 6, of course. For 3, 12, and so on and so forth. For 4, 20. Right. Now, for even m, you can see that this, which is the even part, you go ahead and put even m, so 0, 2, etc., going to be 0 or 6, meaning that this solution is going to be truncated. This is the reason why this is very interesting. And this polynomial is called the Legendre polynomials. Right? Again, for odd m, then the same will happen at the odd part. So if you go ahead and take 1 or 3, so 2 or 12, this is going to be 0. Again, this is going to be 0. So if you go ahead and put m equals to 3, this part is going to blow up, meaning that you only get the solution up until here, right? So you only get a polynomial every time. So that a chosen specific m really dictates what happens to the solution. And of course, for integer m's, then one of these two are going to be 0. One of these two are going to be truncated to a polynomial. Now, let's just check an example and see what happens at m is 1. That means that L1 is 2. And we can easily see that for L1 equals 2, if you go here, this term will be 0, this term will be 0, and all of this term is going to be 0. So this is the only thing that survives. So the odd part is x. This is the Legendre polynomial for m is equal to 1, or lambda is equal to 2. So in general, the differential equation can be written as instead of lambda, you have two continuous multiplicative integers of this form, of this fashion, right? You can likely go ahead and set this instead of lambda. Now, now that we get that out of the line, yes, we know that one of the two solutions are going to be truncated, but what happens to the other solution? Nothing really happens to the other solution. It just stays a series. But of course, you have to go ahead and calculate what this series will be. So, for these specific values, the even term is going to be written as the sum. So what we're going to take, it's better to go ahead and do it analytically. So having the even series as this, if you go ahead and plug lambda is equal to 2, you will have a minus sign outside, which will cancel with this. So what we're going to get is that the even part is going to be the sum from 0 to infinity minus 1 to the 2n, which is 1, over 2n factorial, as before, and the 2 is going to be to create a multiplication factor of this form of 2k, k goes to 1 to n, 2k minus 3 times x to the 2n, right? Now, let's go and compute what that is. Let's see what the k is from going to 1 to n. So we have a two-term acting on k, and this is going to be happening n times, meaning that we have to n, and k is going to be 1 times 2 times all the way up to n, so n factorial. And secondly, let's go ahead and rewrite 2n factorial, which is here. Now this can be written as 2n times 2n minus 1 times 2n minus 2, etc., to 2 times 1, but we can also split these to odd even terms. So this can be written to 2n times 2n minus 2 times 2n minus 4, etc., and all the terms, and all the even terms, 2n minus 3 times up until 3n 1. This, getting again all of the 2's, is 2 to the n and n factorial, while the remainder is just the remainder of all the odd terms, right? So finally, what we're going to have, if we plug it, is going to be the sum of x to the 2n over, let's make a bigger line, so x to the 2n times 2n factorial, and the multiplication of 2k minus 3 that is missing, and in the denominator 2 to the n factorial, and 1 times 3 times all the way up to 2n minus 1. This also goes from k is equal to 1 up to n. So this and this cancels. So what we have is x to the 2n, and this is minus 1 times 3 times all the way up to 2n minus 3, which will cancel with 1 times 3 times all the way to minus 1. So this term and this term is the only one that are going to survive. I think all the other terms are going to be ignored, right? So finally, we have a minus sign, or that will go down in the denominator, so the sum from 0 to infinity of x to the 2n over 1 minus 2n. And this solution are the solutions for lambda is equal to 2. And if you go ahead and plug it, now the Legendre function is going to be written as 1 minus x squared over y prime prime plus minus 2xy prime plus lambda y, but lambda is equal to 2. So this and also x is a solution to this differential equation. And you can easily go ahead and check that. Now let's go and see our code editor and try to write all of this in code, right? Now, let's go ahead and try to replicate our Legendre solutions into Python. So, what we can see here is that we have two different products. So let's try first and treat these terms. So let's define a product that is going to depend on m, so lambda actually, and n, right? The terms. Now we know that lambda is going to be n times n plus n, and we have a product. It's going to be equal to 1, or in our language, MPF of 1. And let's go ahead and run a loop in range. It's going to begin 1 and n plus n. So its factor is going to be lambda, as we know. So both have lambda minus 2 times 2 times k minus 1, which is the same for both of them, and the term changes here. So for the even part we have k minus 1, whereas for the odd part we have k. So this can be written as, so there is a multiplication here, and times we need k when m is odd, so just have this for odd m's. What this means can be written as minus the remainder m, right? And the product is just going to be product, let's call it prod. It won't have the same name, but the function times the factor. And finally, return the prod, right? And now we'll define the Legendre series. I'm going to take n, x, x naught, and m as new parameters, and also define the exponent, because it's different again. So the exponent is just 2 times n plus 0 for this case, or 1 for this. So it can be written as 0 if we have integer, sorry, an odd m, else 1. And finally, the overall factor is going to be minus 1 for both to the n times the product we found of m comma n times x to the exponent, and return the factor over factorial the exponent. That's why we need to also define an exponent, because this and this are the same as this and this are. So now we do have our Legendre series, but we also have an extra parameter. So let's go ahead and add params here and also here, I guess. Right. So now let's try what this does. So for our particular case of, we'll define also an m value. Go ahead and put it to 1. So m value and m equals to m value, and let's go ahead and see what this does. So this is taking a while. Okay, this is taking forever. Let's pause this and send just 1,000 terms instead. So for 1,000 terms at 0.4 and m equals to 1, you get this fine looking number. But we said that our interval of convergence is between -1 and 1. So what happens at 1? Or let's say what happens at 0.9 first? Does it converge? It absolutely does. What happens at 1? Okay, it's 10 times bigger. What happens at 1.1? Now, this is a terrible number, right? We have a divergence catastrophe here, which is but this divergent catastrophe is totally counterbalanced by the even counterpart, by the even solution, which is a polynomial. That is polynomial, right? Now, you could spend many times exploring Legendre series for different types of m and lambda, and it's always fun to do so. But the key takeaway is that there is a lot of stuff going on, meaning that you could play around for hours, and you can always check that the range of convergence that is promised, it is indeed true, and have fun with it, right? Now, let's move on to some lesser examples, and lesser, I mean complex-wise, that we left for last. So let's say we have an example, y prime prime plus 1 over x squared y prime minus constant squared y is equal to 0. Now let's see what happens at 0, right? Xp when x goes to 0 is 1 over x when x goes to 0, and this diverges. What that means is, for the first time, we found a pole that is an irregular singularity. And what we said about irregular singularities is that we do not expand around them, or we do not use Frobenius. But let us do it. So, applying Frobenius, k plus L minus 1, x to the k plus L minus 2, plus AL, k plus L, x to the k plus L minus 3, minus a squared, AL, x to the k plus L minus 2. This is 0. And the lowest term is this. So go ahead and set this to 0. What you'll get is that this is 0. But like we said, this cannot be 0. Or is it? So we get that k is 0. Now for case 0, if we go ahead and, like we know, send this to j plus 2, this to j plus 3, and this j plus 2. If you go ahead and solve what the remainder is, you will get a recurrence relation of this kind, a squared minus j times j minus 1 over j plus 1, right? And for j is equal to 0, a1 is a0 a squared. a2 is going to be to the fourth over 2 a0. a3 is going to be a to the fourth a squared minus 2 over 6 a0, and so on and so forth. The solution will be a0, the sum of x to the n over n factorial and the multiplication factor, like we did in the previous example, of k going from 1 to n, of a squared minus k minus 1 times k minus 2, right? But what that does, so let's go ahead and take our limit, so have a ratio test of uj1 over uj. What this is x to the n plus 1, so not n, x to the j plus 1 over j plus 1 factorial, and j factorial over x to the j, and this goes to j plus 1 squared minus k minus 1 times k minus 2 over the same going to j, k minus 1 times k minus 2. And all of these terms are going to simplify. We'll end up with the limit when j goes to infinity of x over j times a squared minus n times, sorry, not n, j times j minus 1, right? And the most dominant term here is going to be j squared over j, so this goes to j in general. And j goes to infinity, so this goes to infinity. What that does is rendering the radius of convergence to be 0. And what that means is that this series is going to diverge everywhere except at its point of expansion, meaning the series diverges for all, so for all x is different than 0. Now, let's check it to make sure of this in a Python file. Now, like before, we define, let's call this irregular, so and x naught, and let's set x equal to 1, so the product prod is going to be mpf of 1, and for k in range when n plus 1, we're going to have factors. It's going to be a squared minus k minus 1 times k minus 2, right? And of course, go ahead and multiply everything for its factor, and to return, we have x to the n times the product we have over